Linear programming. Our objective is to solve linear programming problems. Who uses this? Landscape architects can use linear programming to determine which plants to plant on a green roof. So let's look at graphing a feasible region. Jillian is planning a green roof that will cover up to 600 square feet. She will use two types of plants, Blue Lagoon sedum and Raspberry Red sedum. Each Blue Lagoon sedum will cover 1.2 square feet. Each Raspberry Red sedum will cover 2 square feet. Each plant costs $2.50, and Jillian must spend less than $1,000. Write the constraints and graph the feasible region. So we have each Blue Lagoon, it covers 1.2 square feet, and the Raspberry Red covers 2, and each plant costs $2.50. We can start with the fact that we can't plant less than 0 plants. We can't plant -1 Blue Lagoons. So B has to be greater than or equal to 0, and so does R. So those are our first two constraints. Now our next constraints are going to be in terms of monetary value and then the quantity in terms of the size that it's going to take or space it's going to take up. So there's 600 square feet available. We can't use more than that because then we're off the roof. So we know that between your Blue Lagoon and your Raspberry Red, it has to be less than 600. So we have 1.2 times B plus 2 times our Raspberry Red must be less than or equal to 600. And last but not least, we can look at our monetary value. So each plant costs $2.50, and we have to spend less than $1,000. So 2.5 times B plus 2.5 times R, and it has to be less than or equal to $1,000. So now we can graph the shaded region. I might suggest using your Y and X intercept, or you can think of it as your Raspberry Red intercept and your Blue Lagoon intercept, and draw them out that way. So take a moment, pause the video, and draw them out. When you return, there will be a graph. And there's our graph. So because we can't plant negative amounts of plants, we have to be in quadrant 1. So we know we've got to be above the x-axis and to the right of the y-axis. And then the blue line goes from our intercept of 300 to 500, and our green goes from 400 to 400, and we shade below on both accounts, which leaves us with this orange shaded region. Alright, so let's talk about bounded and unbounded regions. In the graph that we just had, we had a bounded feasible region. The objective function has both a minimum and maximum value. In unbounded feasible regions, objective functions an objective function has either a maximum value or a minimum value, but it won't have both. So in this one you've got a maximum, but in this one you've got a minimum. So the vertex principle of linear programming. If an objective function has a maximum or minimum value, it must occur at one or more of the vertices of the feasible region. So when you're trying to maximize or minimize a problem, it's going to happen at one of the vertices. You don't need to check every possible shaded spot. It's going to happen at a vertice. Alright, so let's look at solving linear programming problems. So one of Jillian's priorities for the green roof is to help control air pollution. To do this, she wants to maximize the amount of carbon dioxide the plants on the roof absorb. Use the carbon dioxide absorption rates and the data from example 1 to find the number of each plant Jillian should plant. So, this was our graph that we had created in our first example. So now we're going to just take what we had for our first example and we're going to apply it to some air pollution information. So the Blue Lagoon, it does 1.4 pounds of CO2 per year, and the Raspberry Red is 2.1 pounds of CO2 per year. So now we essentially need to create what's called like the objective function. So your objective function in this case is going to be in regards to the carbon dioxide that each of these plants have absorbed. So your C, or for carbon dioxide, equals 1.4 times the Blue Lagoon plus 2.1 times your Raspberry Red. So if we recall back to the constraints that we created in the first example, we're going to end up using those and the graph. So then we're going to look at our graph here, and then we're going to look at the vertices of those constraints that created this graph. So for example, we'll change colors here to green. We have one vertice at 0, 0. So 0, 0 will be a part of this table. Then we have one at 0, 300. And then we have another one at 250 and 150. So 250 and 150. And our last vertice is at 400, 0. So once again, you use the constraints to create the graph, then you look for your vertices. When you find your vertices, you're going to substitute your vertice value, so the 0, 0 in, to your objective function to either maximize or minimize depending on what they're looking for. So for this one, we have 1.4 times 0 plus 2.1 times 0. Well, that's 0. Then we have 1.4 times 0 plus 2.1 times 300. So we end up with 0 plus 2.1 times 300, which provides 630. And now we can go 1.4 times 250 plus 2.1 times 150, and that gives us 665. And then we have 1.4 times 400 and plus 0, because 2.1 times 0 is 0, which is 560. Now, we're talking about Jillian's priorities for the green roof is to help control air pollution. She wants to maximize the amount of carbon dioxide the plants on the roof will absorb. So to maximize, you want the larger number. So therefore, the larger number is 665. So therefore, must plant 250 Blue Lagoon and 150 Raspberry Red. Brad is an organizer of the Boulder 10K race and must hire workers for one day to prepare the race packets. Skilled workers cost $60 a day and students cost $40 a day. Brad can spend no more than $1,440. He needs at least one skilled worker for every 3 students, but only 16 skilled workers are available. Skilled workers can prepare 25 packets per hour, and students can prepare 18 packets per hour. Find the number of each type of worker that Brad should hire to maximize the number of packets produced. So, step 1. we need to get our constraints. So we know if we use x and y, we're going to let x be the students. So we might want to declare this. So x is going to be our students, and y will be the skilled workers. So now let's look at the constraints. Well, we can't have negative amounts of students and skilled workers. So therefore, x has to be greater than or equal to 0, and so must y. 2 constraints down. Now, my hint to you is there are 3 more constraints for this problem. Take a moment and pause the video and see if you can come up with the 3 constraints. When you return, the 3 constraints will be provided to you. Alright, so now we have our constraints. So if we look, we have combined things that are similar. So you have your $40 and your $60 a day, and then you have your monetary value of no more than $1,440. So that would be one constraint because it's one set of information that all goes together. Another piece of information states that, well, we can only use 16 workers. So you can't have more than 16 skilled workers. And the harder one to come up with is he needs at least one skilled worker for every 3 students. I like to think of it this way. At a maximum, 1 skilled worker can equal 3 students, but you can't go any more than that. So a third times x will give you the value for y. Alright. So now let's graph. So take a moment and graph each of the constraints within, and when you return, you will see the graph. Alright, so there's our graph. So we shade below on the purple, above on blue, and below on red, and keep it in quadrant 1 because we have to stay positive here. So now we have our constraints and our shaded region. You might have been wondering, well, what happened to the 25 packets and the 18 packets per hour? Well, that's going to be our objective function. So for this one, our objective function would be P equals 18 packets per hour for a student and 25 packets per hour for a skilled worker. And then we substitute in our coordinates, and we want to either maximize or minimize. If we look in the problem, we want to maximize. Alright, so we have one coordinate being 0, 0. Another coordinate being 0, 16. Another one is 12, 16. And the last one is 24, 8. Usually I go vertically with these and then put the solutions off to the right hand side, but I'm running out of a little bit of room, so I'm just going to write the answers below. So substitute all of your values in and receive your solution. When you return to the video, the answer will be revealed at the bottom. So at the coordinate 0, 0, you end up with 0. At 0, 16, you end up with 400. At 12, 16, 616. And at 24, 8, you end up with 632. So since we want to maximize, the largest value is 632. So therefore, we must hire, or Brad must hire 24 students and 8 skilled workers to maximize the profits. And that ends our lesson on linear programming.